Kia ora koutou. I'm Andrew. I'm another one of the people from Victoria University, as we call it. And today I'm going to be talking to you a little bit about some of our recent work looking at doing explainable unsupervised learning by using evolutionary computation techniques. So I want to start off by talking a little bit about what unsupervised learning is, because a lot of the time when I tell people I do unsupervised learning, they say, oh, you do clustering. Sure, that's part of it, but there's more to the area than just that. So I found this cute little word map that shows you some of the different popular terms in unsupervised learning, so things like embedding, dimensionality reduction, latent spaces, separation, association rules. You can see clustering's in there, but it's more than just clustering. So why do we do unsupervised learning? Generally, we want to explore unlabeled data to find underlying patterns and structure. So if you have a data set, you have no labels for it, you can't do classification, you can't do regression, you want to understand the essence of the data itself. So things like manifold learning or nonlinear dimensionality reduction, where you have some really high dimensional data and you try and convert it to a lower dimensional space, an embedding or in some cases a visualization. And by doing that, you can then understand the data and use it more efficiently. Or also association rule mining, the classic example of buying beers and diapers at the supermarket, which I'm sure you've all heard too many times already, so I won't go through it again, but trying to find relationships between features or attributes in your data. And so really what I'm focused on at the moment is trying to do these things in a more explainable, more interpretable manner. So the first piece of work I'm going to talk about is a piece that we did on visualization, trying to use GP, which a few of my colleagues have already talked about, to do interpretable visualization. So these three plots you see on the screen here, three different visualizations of the dermatology data set, so a nice, reasonably simple data set, but still complex enough. And you can see the three visualizations of quite different qualities. The one on the on the left is quite simple, and there's a lot of overlap between the classes still, so the different colors, different classes. And then when you get towards the right side, you get more separated and you can more clearly see the regions of different patterns in the data. And then above those figures, you see the different trees. So those are trees that we've evolved with genetic programming. And as you might expect, as you get a more sophisticated, a higher quality visualization, you get a more complex model that produces it. So there's this trade-off between having a simple model with a not so good visualization and a more complex model that then gives you a really good visualization. And depending on how well you need to be able to understand your visualization, you would choose a different point in that trade-off. We also did a similar thing, but for more general manifold learning, so looking at not just 2 dimensions, but from 2 to up to 100, 200 dimensions. If you have a data set with 1,000 dimensions, you want to be able to find a good trade-off again between reducing its dimensionality while not doing it so much, but while still having enough dimensions to represent it fairly. And so you can see here that as you increase the number of trees or number of dimensions, your cost goes down, but only to a point, and then you get these sort of diminishing returns. And the classification accuracy has an opposite trend. And again, a really nice thing about the methods we use here is because you find a whole bunch of different solutions at one time, you can find some pretty nice interpretable embeddings. So this is, if you know the MFAT dataset, is 649 features, and by evolving just 12 trees, we managed to reduce it from 649 dimensions down to 12, and that's the 12 dimensions right there. And so you can see the first one's a bit more complicated, but the others are very simple transformations of the original space. And so compared to something like TSNE or UMAP, where you get some really nice output, but you can't then interpret it from the perspective of the original space. And then the final piece of work I want to touch on is kind of an extension of association rule mining to continuous data using a symbolic relationship structure. So these are 4 different data sets, and we tried to find relationships within the attributes, between the attributes in it, and you can get these nice symbolic trees that show you how different attributes in your data are related to each other. Again, quite simple trees, which means you can then interpret them and understand them and hopefully get more insight into your unlabeled data. So thank you very much.